So we begin today then by looking at chapter 14. Chapter 14 is the last chapter that we are going to cover in this class, and it is the chemistry of polymers. And so with a title like this, it naturally begs the question, well, what the heck is a polymer anyway? And the answer is this. A polymer is, for lack of a better term, a heavy molecule. And it is made by linking together chains of smaller repeating molecules in succession. So the repeating unit is called a monomer. Now, in industrial practice, monomers can come in a variety of different forms. My father-in-law, for example, worked for DuPont for about 30 years as just one of the guys on the line. And when I asked him what his job was, he would say, well, we get a whole bunch of monomers that comes in and we put it into the machine and it produces something that we send out somewhere else. Monomers are the building blocks of polymer materials. Now, he didn't know it, but basically that's what he was doing. He was taking starting product and converting it into some kind of finished product that could then be used for some sort of industrial purpose. Monomers are the starting products. We can almost think of monomers kind of like in a train. As is the case many times here in Vincennes, you get caught at a railroad crossing. One of the coal trains runs through. It's got 58,000 coal cars attached to a couple of diesel engines. Those coal cars are all linked to each other to make the train. Thinking of it in polymer terms, those coal cars are the monomers. They are the repeating unit that is linked together to make the train. Now, different trains have different lengths. Sometimes it's not 58,000 coal cars. Sometimes it's only 35. Sometimes it's 80. I had one student in this class actually a couple of years ago explain to me, well, I ended up being about 10 minutes late today. And the reason was I was stuck out on the train track on 2nd Street and a 115 car train went by and basically I was stuck there. I couldn't move. I said, you really counted 115 cars? He said, I had nothing better to do. So polymers are made by linking together smaller units in succession. And because polymer lengths can vary from sample to sample, it's sometimes difficult to get a true sense of how big they are. Now, we will refer to polymers broadly as macromolecules. Macro meaning large. And that's pretty good description. They're large molecules. Now, common examples, believe me, there are lots and lots of examples. Most of the things that we encounter actually have polymers derived in them somewhere. Things like plastics, synthetic fibers, which probably most of you are wearing some form of right now. Things like polyester, nylon, rayon. In more extreme cases, things like Kevlar. Rubber-based materials, foams. All of these things are polymers. And the majority of these polymers are actually derived from one source in particular. Anybody know what the primary source for most polymer materials is? Josh? It's not silicon. It's crude oil. It's not a well-known fact that the majority of the material that comes from crude oil is actually used to make plastics and other polymer materials. Very, very, very small percentages of it are actually used to make things that we usually associate with crude oil, like diesel fuel and gasoline and other kinds of fuel products. The majority of the stuff that we get from crude oil ends up going into making plastics primarily. Plastic recycling helps with that to some degree, but the feedstock is just too great. We need far more plastic on a daily basis than ever gets recycled. And a good bit of plastic is unrecyclable, and even the stuff that is good oftentimes ends up just getting burned because, well, it's not good enough to turn into anything useful. It's too badly contaminated or damaged. You can't just chop it up and turn it into something else. So a lot of fuel companies end up just burning it and at least turning it into some amount of electricity, along with a whole bunch of other byproducts. When it comes to polymers, there are a number of different kinds, number of different ways that we can classify them. One of the ways that we can classify them is based upon some of their common physical properties. And that's where this distinction comes in. Thermoset polymers versus thermoplastic polymers. Thermoplastic polymers are the ones that we're the most familiar with. These are the ones that, in the process of making them, they will soften upon heating. That allows us to mold them into a variety of different shapes, different conformations. But when they're cooled down to the normal temperature, they can form relatively rigid kinds of materials. And the kinds of plastics that are in this are, well, like I said, they're mostly plastics. Polyethylene, polypropylene, polystyrene, polyvinyl chloride, PVC, and peat. You know these better as peat, number one, plastic. Polyethylene comes in two different forms, high density and low density. They make up number 2 and number 4 plastics. Polypropylene is number 5 plastic. Polystyrene, you know better as styrofoam, which is number 6 plastic. And PVC, well, that's the kind of the plumbing flavor of the millennium right now. Lots of metallic piping is being replaced with PVC in a number of different locations because of its rigidity and its sturdiness and its lack of corrodability, which metal pipes inevitably wear out over time. PVC is less prone to that. Thermoset polymers, on the other hand, once they are solidified, once they take their cooled and final shape, we can't do anything with them. They can't be remolded. They can't be turned into anything else. As a result of these kinds of polymers aren't often very recyclable. We can reuse some of them. So in the case of vulcanized rubber tires, we can reuse or repurpose them. Anyone that watches a football game now sees one of the common uses for repurposed tires. They grind them up into little bits, and that becomes the softer padding on most types of artificial grass nowadays. They've also been repurposed for things like playground paddings and other things like that. But for the most part, things like polyurethane, fiberglass, electrical insulators like Bakelite, Not a whole lot of repurposing that we can do with those. Once they're used, once they're done being used, not a whole lot of recycling we can do with them. There's not a whole lot of repurposing that we can do for them. Their limitations in that regard are pretty severe. But they are thermoset polymers. Once we mold them, they can't be unmolded. They are locked into whatever shape, whatever conformation that they're put into, which makes them really durable in that kind of sense as well, though. Some of the things that we have to be concerned with regarding polymers is that because they are carbon and hydrogen based for the most part, they are flammable. And when most of them burn, because there are other elements involved besides carbon and hydrogen, they usually are going to generate some kind of toxic gas. And even if it is just a hydrocarbon, even if it is something like polyethylene, which is just carbon and hydrogen after carbon and hydrogen after carbon and hydrogen, even in that case, because the molecule is so big, it has so many carbons to burn through, there can almost never be enough oxygen present to get a complete combustion. And when we don't have complete combustion, what is one of the common byproducts? Carbon monoxide. Carbon monoxide, as we talked about in chapter 10, pretty toxic gas. Because polymers are so prevalent, they're everywhere. Look around this room, you'll find many, many, many different polymers. Right now you're sitting on one. Your feet are touching another. Your notebooks and pencils are resting against one. Half of the stuff on my desk here is some sort of polymeric material. Because they are so common, pretty much every fire involves some kind of polymer burning. One of the primary reasons why most Class A fires end up being incomplete combustions. There's just not enough oxygen present to burn through all the material, at least not efficiently. Now, in addition to classifying them by their physical properties, we can also classify polymers based upon how they're used. And that breaks down into two, maybe even three different kinds of categories. There are the plastics. These are the ones that are usually thermoplastic. They can be formed and molded and shaped into a variety of different forms. There are fibers, polymers that can be produced as threads, yarns. They can be woven together or knitted and make a variety of different fabrics, other kinds of textiles. Some of these fibers are natural fibers. Silk, for example. Silk is a naturally occurring polymer that comes from a certain type of insect. A variant of silk is found in spider webs. Those are naturally occurring polymers that are made by those animals' bodies. So it doesn't necessarily have to be something synthetic. There are natural versions of these. Wool, for example. Wool is almost kind of like a biological fiber. Not quite the same, but very, very, very similar. We also have something called an elastomer. Elastomers are kind of interesting because they have a very interesting kind of molecular shape that allows them to, it's almost kind of like a slinky. You're familiar all with the slinky spring toy. You can kind of pull that slinky apart. And as you pull it apart, it's going to elongate, it's going to get bigger. But when you remove the stress of you pulling on it, it snaps back together, kind of like a rubber band. Elastomers are substances that when we strain them, we can stretch them, we can unwind them, they can get longer. But when we release that tension, it goes back to the original form. As you might imagine, based upon this prefix, we're talking about a lot of elastics here. Spandex. The stuff that goes into your elastic waistbands in different kinds of clothing, sweatpants, even dress pants usually have some elastic material in them to allow them to be put on more easily and taken off more easily. Those elastic materials usually do have a shelf life, as anyone who's ever owned a pair of sweatpants or shorts knows. You wear them enough times, eventually those fibers elongate to the point and they just don't spring back as much as they used to. That is, they are elastomers that are being used there. So any kind of elastic material, anything that is stretchy. So a lot of clothing, especially in the past, I don't know how long have leggings been a thing? 5-10 years maybe. That whole industry around Spanx and leggings, jeggings, all that stuff that's based upon materials that are meant to stretch around a person's leg, around a person's body. Those are all derived from some form of elastomer or another. When it comes to naming polymers, we usually attach the prefix poly in front of the substances, and these substances are the monomers, when we make specific polymers. So for example, the name for that particular compound there is vinyl chloride. If I link together a whole bunch of those vinyl chlorides together, the resulting product would be something called polyvinyl chloride. Polyvinyl chloride, better known as PVC, is one of the more common polymer materials out there. And again, it has a lot of different kinds of uses. Now, when it comes to these polymers, how we go from this to a long chain of these is through a process known as polymerization. And understand this molecule here on the right is only the result of linking together 3 of the vinyl chlorides. When it comes to polyvinyl chloride, the compound, we are likely talking about hundreds, if not thousands, of these vinyl chlorides linking up together to make this polymer. So this chain goes on and on and on and on and on and on and on. Now, polymerization is the way that this happens. It's kind of an interesting chemical reaction because what we're going to see is that the monomers that are ultimately going to create polymers can't be any old compound. Certain types of compounds have to be available, have to be present in order for a polymerization reaction to occur. Now, ordinarily, these kinds of substances that we're talking about usually are ones that have electrons that are free and willing to move. So in the case of a lot of these, what we're talking about is that double bond. So if you look at the structure of the vinyl chloride again, that double bond there in the vinyl chloride is a place where electrons can be free to move a little bit. Because if I tear apart that double bond and make it a single bond, the molecule still stays together, but now there are 2 more electrons that are free to do something else. And that something else is usually the creation of a new bond. Now, once they create these chains, lots of different things can happen. It is very rare that these chains are just going to form these long parade ground trains of hundreds of molecules lined end to end to end and have nothing happen to them. It is far more likely that the chains will start to attract either other chains or attract some of the other atoms within their own chain and form folds, coils, loops, stacks, any kind of intertwined, three-dimensional kind of shape. Now, in your body, a similar process goes on when your body makes proteins. Proteins are probably the closest thing biologically that we have to polymers. In proteins, instead of monomers, what we have are amino acids. Those amino acids can stack one after another to make the sequence for a protein. But those amino acids also attract other amino acids and can form loops and folds and sheets and bends and do a lot of different things to end up making a three-dimensional protein. That's the kind of stuff that happens inside of your body. That's how we make certain types of proteins. Those proteins that can be used to do a number of different biological functions inside of your body. Polymers act in a very similar kind of way. They will attract each other. They will begin to form loops and bends and folds and turn that long spaghetti strand chain into something more resembling a three-dimensional object. The chain itself forms through a polymerization reaction. The polymerization reaction usually takes one of 2 forms. The first is something called an addition polymerization. In addition polymerization, what we usually see are monomers linking together one after another, after another, after another. Usually happens where we've got some kind of an alkene. So let's take ethylene here for an example. Some kind of compound comes in, usually called the initiator, and that initiator takes one of these electrons away, which means I've got one electron left over, and that electron goes out, does the same thing to the next ethylene molecule, does the same thing to the next one, and to the next one, and to the next one. And before we know it, we've got this long chain of ethylene molecules linked all together. As a result of this, polyethylene, polypropylene, all of these addition monomers will form their polymers and have no byproducts left over. All that will come out of this is we will get our initiator back. The initiator basically acts as a catalyst. Comes in here, takes an electron away, and then somewhere later in the process, the electron comes back to the molecule, and the initiator drops out. Using our train example, this is kind of the thing that we see when that coal train runs through. Car after car after car after car of coal. No breakups in the action, it's all coal. Condensation polymerization is a little bit different. Instead of a single polymer, what we usually have instead are alternating monomers. Those monomers usually will have one of two endings. So they will either end with an acid, like so, or they'll end with an amide, like so. And usually on the other end, we've got some kind of an alcohol group or something similar. What happens is that as these link up, we will see the hydrogen from the one group link up with the oxygen and hydrogen from another, and that'll give us water. Or we will see, in a different case, the hydrogen from one group link up with the NH2 of another group, and that'll give us ammonia. But because these reactions occur, and because they are giving us small molecules like ammonia or water as byproducts, what we will see in these is that they have to alternate. The molecule on the left links up to the molecule on the right, which attracts the molecule on the left, and then the molecule on the right, and then the molecule on the left, and then the molecule on the right again. This is more like those freight trains that come through town, where I've got maybe a stack train car and then a car carrying chemicals, and then a stack train and then a chemical car, stack train, chemical car. They alternate one after another after another. It's still a polymer, it's still a train, but it has a different kind of construction. So continuing with the train kind of analogy here. You can see that for an addition polymer, we're talking about consistency. All of the freight cars in the train look exactly the same. This usually gets started by an initiator that goes and steals an electron. That electron that is left over goes and steals an electron from another monomer, which steals an electron from another monomer, which steals another electron, which steals another electron. And before you know it, you've got a train, a long chain forming. At some point in time, this initiator will end up getting chopped off, leaving behind the pure polymer at the very end. These kind of addition polymers are usually ethylene derivatives. Meaning that they're going to have two carbons that are double bonded together with hydrogens everywhere else except for one location. That one location there we call R, and it just signifies that that group there is variable. It can be another hydrogen, as in the case of ethylene. It can be a carbon, like CH3. That's where we get propylene. It can be an oxygen group. It can be an alcohol group. That would give us polyvinyl alcohol. It can give us chlorides, bromides. There are lots of different things that can go in that R place. And the result of it is pretty simple. The result is we're going to get a addition polymer that has that unit repeating over and over and over. Condensation polymers, on the other hand, are alternating train cars. Again, usually what we see in these kinds of polymers is that we have either an acid group like this, or if we replace this OH with an NH2, it becomes an amide group. So that's usually one of the cars. And then the other car is usually some kind of an alcohol. And what happens is we end up creating these linkages in between. These linkages are chemically known as esters. And so since that is our repeating unit, the ester, condensation polymers are broadly referred to as polyesters. So the term polyester does not refer to a single kind of compound or a single polymer. It is referring to a class of polymers that have this particular kind of linkage in them. And that is what makes them kind of unique and different. So like I just said, since each of those monomers is linked to each other by an ester group, these are polyesters. Now, in addition to these, we also have something known as a cross-linking polymer. Cross-linking polymers are usually thermosetting. And because of their thermosetting characteristics, their chains tend to be a little bit weaker because they don't have as much flexibility. One of the things that we can do to combat that is something called cross-linking. Cross-linking involves taking those polymer strands. So let's just imagine for a second that I've got these chains of polymers here. If they stayed in this state, those chains would just kind of slide over one another. And as a result, they wouldn't have a whole lot of stability or structure to them. What cross-linking does is it introduces some kind of a chemical compound that puts bridges between the polymer chains themselves and makes them less liable to move. That is going to decrease their flexibility, decrease their ability to just kind of slide over one another, and increase the rigidity and their strength. One of the most common derivatives of this is silly putty, slime. Probably the most common form of slime out there is polyvinyl acetate slime, Elmer's glue, where you treat Elmer's glue with a solution of borax solution. And the Elmer's glue goes from kind of this slightly sticky, because you add some water to it, solution to this rubber ball-like compound. If you've never done that particular type of slime, it is featured in your lab for next week, that you'll actually get the chance to make that slime and kind of play with it and look at its different kinds of properties. The process involved there is a cross-linking process. The reason why the Elmer's glue is slippery after we add some water to it is because the polyvinyl acetate strands just kind of slide over one another. As we add that borax, we're introducing borate ions as cross-linkers, and that's going to strengthen up the structure, cause those polymer strands to seize up a little bit and take on a more solid-like kind of consistency, as opposed to a purely liquid-like consistency. In chemical terms, that's what I was just talking about. This funky looking molecule here is the borate ion, which is what is found in borax. Another common application, vulcanization in tires. So natural rubber is kind of soft, sticky. When we treat that natural rubber with a series of sulfur compounds, those sulfurs actually act as cross-linking agents between the sulfurs, or between the rubber strands, and the rubber goes from this kind of sticky residue sap-like consistency to this hard rubber rigid kind of consistency. So that's kind of what cross-linking can do for us. And that's where we'll stop for today. So on Monday, we will talk about autopolymerization, talk a little bit more about kind of the general chemical makeups of polymers, and then we'll start getting into some examples. Have a great weekend.